Great. Welcome back, everyone. Thanks for joining us again. For our next talk, we have an invited talk by Jibran Rashid. We're very happy to be hearing about computational contextuality today, a topic that I know far less about than Jingbo's topic. So thank you very much, Jibran, for joining us, and I'll hand straight over to you. Thank you.
Thank you very much, Peter, and thank you for the organizers for inviting me to the conference. So yeah, computational contextuality is something that we are proposing as another perspective on the standard quantum contextuality model. And hopefully by the end of the talk, I've motivated enough how can we build or what exactly is computational contextuality. So this is joint work with Abu Zer at University of Latvia and Muhammad Adil, who's my graduate student at IBA. All right, so the way I'll motivate or start off the talk is actually by introducing the standard example of quantum contextuality. And one of my favorite examples is the Mermin-Perez square. And so here, if you bring in the computer science perspective within this example, we can look at it as a game where a verifier and a prover are interacting with each other. And the idea is, let's say that there are 9 variables, binary variables. So we label, we think of A1 up till A9 as values between +1 and -1. And we want to assign each one of these 9 variables a value, +1 and -1. But the rules of the game are that the referee will actually not ask for all the 9 values from the prover. The questions that are allowed to be asked, and you can kind of already see where it's coming from in terms of its links with quantum, the questions that could be asked are only what we call R1, R2, R3, C1, C2, C3. And what they are defined to be are essentially just products of the corresponding rows and columns. So R1 then is defined to be A1 times A2 times A3. Correspondingly, R2 would then be A4 times A5 times A6, and so on and so forth. Right, hopefully the definition is quite clear. Similarly, C1 is A1 times A4 times A7. Now, the rule that is being provided by the referee is that the assignment that is given to these 9 variables should satisfy the condition that R1, R2, R3, doesn't matter what the actual explicit value for each A1, A2, A3 is, as long as the product of the 3 is 1. Same thing happens for row 2, same thing happens for row 3, same thing happens for C1, same thing happens for C2. But for C3, the rule changes and we ask the value to be -1 for the products of the 3rd column. All right. And now we ask, hey, does there exist a deterministic assignment to these 9 variables that satisfies this condition? So that's the rule. And you just look over the condition for a little bit and convince yourself that that's not really going to be possible, because you can kind of individually consider the 3 rules corresponding to the rows and the 3 rules corresponding to the columns, and identify that the row rules are essentially just saying that R1 times R2 times R3 has to equal +1. Because each R1, R2, R3 themselves have to evaluate to +1, whereas the rules for the column then say that C1 times C2 times C3 has to equal -1, because it's kind of got odd parity, because the 3rd column has to evaluate to -1. And now you realize that C1, C2, C3 is nothing more but just the product of A1 to A9. So is R1, R2, R3. And so you've got this now contradiction that, hey, there is no satisfying assignment, because the product in one case ends up being +1 and the other case ends up being -1. So there is, the conclusion then we draw is that there is no deterministic assignment to these 9 variables or classical assignment to these 9 variables that satisfies our requirement. The quantum connection then comes in is that if we treat these values of these variables as physical quantities and physical observables, then here's a possible assignment of these 9 variables corresponding to the observables that the party can measure over 2 qubits, let's say. And note that the actual this is a state-independent example of contextuality, so it doesn't matter what the actual quantum state is. This operator solution corresponds to exactly the requirement, and you can verify this, that when you evaluate the product of the 3 observables in the rows, you get the identity matrix. Same thing for the 2nd row, same thing for the 3rd row, and column 1 and column 2. But for the 3rd column, you end up getting minus identity. And so this assignment of observables to A1 to A9 exactly satisfies the condition that we identified at the beginning. And this was proposed by Mermin and Perez as an example of question specters kind of sets that are example of contextuality, right? And so we won't get into kind of the historical evolution of contextuality and how it's been discussed in the literature. What we want to kind of relate to it is to start off how people considered, well, just like non-locality can be considered as being classically simulated by, if you allowed communication between the parties, what would be the corresponding resource that allows for simulation of these correlations in the classical case? And so what we end up showing, well, other people already showed that you can use classical memory as a resource. And so you can treat the classical memory as what you would have initially thought of as hidden variables. And Kleinman et al. Proposed kind of this model where you want to treat these kind of three S1, S2, S3, S3 classical states, where each individual state in of itself kind of is keeping in its own account 3x3 table. The way to read this 3x3 table is that if the classical device that we have built, let's say, is initially in state 1, and it is queried regarding, let's say, the first cell of the 3x3 Mermin square block, the answer it will kind of give out is +1. And it will stay in the state 1. Now, if the second entry is asked, it will, from the first row, it will also output +1. But then if now the third entry from the same row is asked, it will output +1, but the state itself of the device, the internal classical state, will transition to S2, such that next time when you ask a question, the outputs will be derived from the internal table of the state S2 rather than S1. And so you can verify yourself that this evolution, this transition evolution between S1, S2, and S3, and the outputs that will be produced will actually end up satisfying the correlations that were required by Mermin Perez. And at this point, it's nice to kind of stop and also ask, well, when we initially saw the classical impossibility proof that there exists no deterministic assignment to A1 to A9 that satisfies the 6 constraints we had, why exactly is it that the quantum case does not violate that proof? And part of the answer is the fact that we note that the rules themselves are kind of rigged in a way such that it satisfies this issue that within this 3x3 grid, each of the questions corresponds to a row or column where the corresponding observables are all compatible. So you can actually simultaneously measure every entry in a row or every entry in a column, whereas that's not going to be true if now you ended up asking a question on the diagonal. So observables on the diagonal are not commuting. So in essence, the quantum solution is still not guaranteeing a deterministic assignment of all the 9 values at the same time, because, well, not all the 9 values are going to commute with each other, so they are not all simultaneously measurable. But if the experiment was already defined to say, hey, I'll only ask these rows and these columns as my question, then the game is already rigged such that the quantum solution works out. Note that that's not true for the classical hidden variable model, right? In the classical hidden variable model, you could potentially ask any individual entry as many times as you like in any order you like. Right, so this became an example of how you can now develop a relationship between an example of quantum behavior, uniquely quantum behavior in form of quantum contextuality, as in this Mermin Perez square, and then ask about, hey, the kind of correlations, the kind of quantum behavior, the kind of statistics that you're generating from that model, how can they be classically simulated? In this case, we identify classical memory as a resource, and that becomes kind of the interplay between the two. You get a quantum example, you ask the question, hey, what's a quantum memory model that will allow you to simulate this? And that's a very natural question to ask. Could we actually always do this for any example of quantum contextuality? So the specific example in this memory model that's used over here is nice and simple because it's actually what you would call a finite automata model, that there is exactly a fixed amount of memory in the classical model. So you could ask the question now that if I'm given an arbitrary quantum contextuality example, would it always be possible to simulate it with a classical finite automata? And we know that the kind of example, so Mermin Perez square is not just one unique example. People have kind of generalized this class of games to what's called the binary constraint system games. And it is possible to consider for this class of games a finite memory model, but the binary constraint system games are only just one class again of quantum contextuality game. And we're asking, is it always possible to simulate such quantum contextuality with finite memory models? And the answer we will give already is no. And the way we do it is by first taking a slight detour and saying, hey, just like we were considering classical finite memory models, you could also define a quantum finite memory model for computation. So this is a much simpler model of computation than the way we think about quantum circuit models or quantum Turing machines. And so in some sense, it's kind of nicely suited to ask simpler questions regarding potential power of quantum computation models. So there's a question in the chat, let me read. So we are not considering classical memory as a constraint. We're considering classical memory as a resource for allowing a classical player or a classical entity to simulate the correlations defined by the Mermin pair square. Right? The constraints are defined independent of whether the player is a classical player or a quantum player. The issue is more that here's a defined rule for the game, and now you ask, how can a quantum player play the game? How could a classical player play the game? And the takeaway then from the previous slide is that a classical player could also satisfy the rule as long as you're not asking them to just work with 9 bits of memory. If you allow them kind of an internal additional set of resources in terms of memory, then they can also generate the same correlations that the Mermin pair square is generating. And now the question we're asking is it always possible for them to, or for a classical player to develop a finite memory model to simulate a quantum contextual example to begin with, right? Is that okay? All right, so I move on. So the details of the quantum automata, we need not worry about it. The idea is just like in the classical finite memory model, classical automata model, we are restricting the entity, the device, to have only a fixed amount of classical bits, classical memory. And then there are transitions between those different states of memory. Similarly, you can now then say that the device also has a fixed amount of quantum memory. And so for our example, perhaps it would be sufficient to just consider 1 or 2 qubits that the device has. And the device allows for the possibility for you to apply a unitary evolution to the quantum memory that you have, and then perform a measurement on it. All right. And there are lots of nuanced distinctions of various quantum automata models that are defined in the literature, and we won't necessarily delve upon them during this talk. They do result in different computational powers, but for the moment we won't worry about that. And the takeaway from already existing research on quantum automata is that we already know from a result in the early, or actually late 90s by Mbinus and Watrous, that there exist languages. You can think of languages as essentially just problems, where there exists a quantum automata that solves or decides that language, whereas there exists no classical finite memory model that solves or decides this language. So one of the nicest, simplest example is this case of what's called palindromes. You might already be familiar with it, so consider all, so if an alphabet is just the symbols A and B, and we now consider the set of all possible strings that you can build using these characters. The set of palindromes will be the strings that are same forward and backward. So A, B, B, A would be a palindrome, B, A, B, A will not be a palindrome, right? So the string equals the reverse of that string. It's known that classically, if you need logarithmic amount of memory in terms of the input string size to be able to decide whether the string is a palindrome or not. But you can't do it with a fixed finite amount of memory. So if you just say, hey, I'll give you a fixed number k bits of memory, but now I will allow or I will require that you take a string of arbitrary length and identify for me whether that string is a palindrome or not. That's not possible to do with zero error classically. Quantum mechanically, and Mbinus and Watrous have shown by this result that there does indeed exist just a single qubit, in fact, so a quantum automata using a single qubit that satisfies or decides palindrome. There is a one-sided error in this model that you can make as small as you like. Again, we won't worry about that for now. So what's the takeaway from this? The takeaway we could kind of say is that we could imagine that in this case, the problem of palindrome and the statistics that this quantum automata is generating via solving this problem of palindrome are then again a question that we ask, hey, is it possible to simulate the correlation answers generated by the quantum automata on palindrome via finite classical automata, just like we did earlier in the Mermin-Perez square. And here the conclusion would be no. Because we know of a classical memory separation between palindrome for classical automata and quantum automata, it is not possible to simulate palindrome classically with any amount of finite memory. So it becomes kind of a nice kind of impossibility result that even though we have some examples of quantum correlations that can be simulated via finite memory models, there do exist other cases which cannot be simulated. There are more kind of technical nuances in terms of the model of memory access that we are using that we'll talk about more, right? But the key takeaway, the key observation that we want to use over here then is you could take, and there are multiple, I'm just citing one example over here, there are multiple different separations known between different models of quantum automata and different models of classical automata. And all of those examples then could be rephrased as models in which we are saying classical fixed memory model is not able to simulate a given quantum correlation, right? And we want to then ask this question in a slightly different way than just like for a quantum computer, we ask, well, if there is a quantum algorithm like Grover's algorithm, Shor's algorithm, what is the key ingredient in that algorithm that is giving it its quantum advantage over its classical counterpart? Similarly, in all these separation models now between a quantum automata and classical automata, what is the key ingredient that is giving these quantum automata models their power over their classical counterpart? And so now we turn our way around. Initially, we looked at how quantum correlations were simulated by classical memory, and now we kind of go the other way around and say, hey, when there exists a quantum automata that cannot be simulated by classical memory, is it possible to extract from that model an example of quantum contextuality? So that's what our final conclusion would be, and that's what we're kind of terming as computation contextuality, because any computational model then where we are generating correlations that cannot be simulated by a classical fixed finite memory model can be then turned around and be taken as, or we could extract from it a model where we identify quantum contextual correlations. And what's not clear necessarily right away, right from the bat, is how do you extract the context within those correlations, right? So for example, in the Mermin-Perez example we saw earlier, what is in fact one of the key ingredients of contextuality is this notion that, hey, there were these two contexts within which these observables could have been measured, right? So the first entry could have been probed by either doing row 1 or column 1. How do you identify that kind of compatibility structure in an arbitrary separation result between a quantum automata and classical automata? And that's what I'll kind of provide as an example of next. So here's a much simpler separation result between classical and quantum for a promise problem. So previously we looked at cases for example, in the case of palindrome, where the input string was any arbitrary string over the characters AB. A promise problem within computer science is where you place an additional restriction that the input strings that you're going to get are then going to be a subset from the universe of all possible strings. You're not allowing all possible strings as input. You're promised that the input string that you'll get is already from a smaller subset. And so in this case, the two subsets, so first of all, we're only looking at the unary alphabet. So the only symbol we are looking at is, or the strings that we will make will be just a sequence of a bunch of A's. But now we are not allowing for any arbitrary length string. We are saying that we are going to partition these strings, or the input string could be from one of these two possible sets. So either it's going to be an even multiple of the power of 2, so that's going to be the length of the number of A's that I have, or it's going to be an odd multiple of the power of 2. And the question we would like to ask is the given input string an odd multiple or an even multiple? So if it's an odd multiple, answer yes. If it's an even multiple, then answer yes. If it's an odd multiple, then answer no. All right, is the promise problem okay? Right, I'll take it, it's okay. And so then there's a very simple 1-qubit solution to deciding this promise problem. Assume you've got a 2-qubit system within Q1 and Q2, you can think of them as 0 and 1, and just apply rotations by pi over 2 to the k for whatever string that you have. K, recall, is actually an input parameter of the promise problem that you're looking at. So you identify k as the input parameter And so given that you know K, you are now going to basically say, as you start reading the input string that is given to you, for each single A that you see, apply a rotation by angle theta. And so this now then guarantees that once you see the first n, where n is equal, capital N equals 2 to the k, first n number of A's, you would have transitioned from Q1 to Q2. And similarly, then after an additional n number of A's, you will have transitioned from Q2 to minus Q1 to minus Q2 then, and then Q1 again. So that would complete your full cycle. And so you get the possibility, and then that the way we set up the rotation and the way we have set up the promise for this problem, you're guaranteed then that whenever you will perform these n rotations, after performing those n rotations, you're guaranteed to be in one of these 4 orthogonal states. And so this now uniquely allows you to identify that, hey, when I'm in Q2 or minus Q2, the number of rotations I've seen, or the number of A's that I've seen, are an odd multiple of power of 2, and Q1 and minus Q1 would correspond to an even multiple of powers of 2, right? So that then becomes a simple way to decide this promise problem using a single qubit. At the same time, we also know that this promise problem can be solved, or to solve this promise problem, you need at least 2 to the k plus 1 classical states to solve this problem. So again, quantum mechanically, we can do this using a single qubit, whereas in the classical case, you need an exponential number of states to be able to solve this problem. So that becomes your separation. Any questions so far? Nada? Okay. So the last main thing then I'll show then is where exactly are we extracting the contextuality from here? And we chose this specific example because it's a nice simple example to argue about how to extract the contextuality, because you note that because of the structure of the problem, you always end up essentially measuring in the Z basis. That's all you need to worry about. You are not measuring in any other basis. You just end up measuring in the Z basis. And that's sufficient to extract your results with 0 error. And so for the quantum case, then in some sense, it seems to be the extreme case where, there is no incompatible measure involved, regardless of the input you get for your problem. All the measurements are going to commute with each other because all of them are trivially the same measurement. So how could we build an example of a game just like the Mermin-Perez exam previously? So what we'll relate it to is, because the separation exists, assuming that the classical player has some fixed amount of memory. So let's assume that the classical player has classical m bits of memory. And so we imagine then, analogous to Mermin-Perez, constructing an m by m kind of grid of variables. So you imagine each of these entries in this m by m table will correspond to a string from the promise problem, where we would ask, hey, is this string an even multiple or an odd multiple? And then based on the memory separation that we know, we could just say, if the classical player has m bits of memory, that means that the maximum number of states that they can have are 2 to the m. So we now just need to guarantee that we choose k such that the classical memory won't be sufficient. So we can choose k to be any value greater than or equal to 2 to the m plus 2. And because we know that it requires 2 to the m plus 1 states can be simulated, but 2 to the m plus 2 states cannot be simulated when the classical player has just m bits of memory. And now you can just choose I to be all possible values between, or iterate over all possible values between 1 to m squared, and assume you kind of pick a unique value of I for each of the individual entries within this m by m table. Right? So essentially, you've got m squared questions within this table, and now you ask the question to the player, hey, give me the answer to any single row or any single column. Because of the previous separation result, we know that any classical player will not be able to answer all of the questions correctly, because if they were able to do it, then the separation doesn't exist anymore. As at the same time, in the quantum case, the player is able to extract all these answers. In fact, now this is, as mentioned, an extreme case where you do not even need to have this issue of the quantum player only being restricted to ask a single row or a single column, because all the observables are going to commute in all the m-square entries, then you can literally even ask for a complete assignment for all the entries. And naturally, this is not going to be something universal. So it just happens that for this very simple problem, you ended up with a quantum solution where the observable is commuting for all the possible input cases. In fact, if you go back to the palindrome example, there it is the case that for all the yes answers, it ends up still being a computation basis measurement, but for all the no answers, it won't be necessarily a computation basis measurement. And then, so what kind of is interesting there to work out is how do you construct the corresponding kind of grid such that you are linking within the grid in a given row or a given column only compatible measurements, right? Because you can't guarantee necessarily that all questions will be yes questions within a single row or single column. So how do we pick those entries? And that's, we could do it on a case-by-case basis, but so far we don't have necessarily an algorithm that would allow you to do it for an arbitrary problem, right? So that's then an example of how we are building computational contextuality, which seems to have a very different flavor from a standard contextuality example. It introduces this entire algorithmic aspect of doing a computation for solving a problem, in addition to the initial quantum kind of notion of, hey, do these 9 variables kind of coexist at the same time? Are these 9 variables possible to measure at the same simultaneously? Are these 9 observables simultaneously measurable? All right, and this kind of relates nicely to two other things. One is Peckins has proposed this operational theory for studying contextuality, where you divide up an experiment into this notion of preparation, transformation, and measurement. And then you can talk about contextuality at the preparation level or the transformation level or the measurement level. And what I was intrigued by is that if you look at contextuality in this computational way, then any such experiment nicely just transforms also into a computation in terms of input, computation, and output. So would there be kind of a direct link or equivalence between building contextuality in terms of these operational theories and building contextuality in terms of these computational models? And then the additional issue brought up with these examples of contextuality, in the previous case, like Mermin Perez, there was no notion of time complexity in getting your contextuality back, right? You just had observable, you measure it, and that's it. Whereas now, so here's an example of another promised problem for which we know for memory separation between classical and quantum memory models. However, the quantum model only works in exponential time. That's why I shouldn't say only, but so, the issue is even though you get kind of a benefit in terms of only 1 qubit needed, but the drawback is that the amount of time it will take for you to extract that answer, which is to implement the algorithm on that quantum memory, takes exponential time. So this notion of, hey, it's taking exponential time to extract the measurement result out, how does that interplay with the notion of contextuality? It's something to consider. We haven't explored it yet. And so since we're nearly out of time, the kind of different directions we can move forward with is one, to identify then general routine for constructing different contextuality examples given a memory separation result, right? So this essentially is pointing to the fact that in our example, we were able to build a full M by M grid where all the measurements were commuting. That will not be the general case for an arbitrary separation result. So how do we go about constructing the corresponding context for that separation result? Is there an algorithm for that? Contextuality has been studied recently within graph theoretic models such as hypergraphs, Peckins operation model. What's the relationship between this proposed contextuality model and others in the literature? So very recently, there was an experimental kind of paper on computing symmetric functions using only a single qubit on IBM's processors. And so that was given as an example of quantum advantage. It would be interesting, but that was looked at in the quantum circuit model. It would be interesting to see whether or not contextuality shows up there as well. Last kind of interesting point is this notion of, so people have looked at noise robust contextuality, right? Where the idea is, rather than looking at perfect cases, you want to ensure that even in the presence of noise, the contextual correlations that you're deriving are robust against that noise. How does that interplay with the fact that within the memory separations that we're getting from computer science, we have these notions of bounded error separation results, where you say, all right, the automata would actually allow, or you can make the error as small as you like, given that you repeat the algorithm some number of times. How does that relate to noise robustness would also be interesting to study. And with that, I'll finish the talk. Thank you very much for your time.
Thank you very much for that, Jibran. Just on time. And we have just one question in the chat here. If anyone else has got any, put them in, post to everyone. The one question written there at the moment is, so why is classical memory considered a constraint? Shouldn't the final measurements of any quantum system give out classical results?
So I kind of referred to it during the talk already. So the classical memory is not a constraint here. The classical memory is actually a resource. So the notion, going back to the earlier example, where we are using classical memory. So here the classical memory is not a constraint. Here the classical memory is the additional classical memory, rather, I would say, right? Because initially you can think of A1 to A9 as your classical memory. And then we are saying, hey, there's no deterministic assignment to just these 9 variables that satisfies the constraints. Let me give them these additional classical states, S1, S2, S3, which internally themselves store this entire 3x3 grid. Then having this additional classical memory does allow them to, the device to generate the correlations predicted or required by Mermin pairs.
Great, thanks very much for that. It doesn't look like there are any other questions, and we're also on time anyway. Jibran, Rashid, thank you very, very much for that great talk. We now have a half-hour coffee and tea break, and then after that, 2 more invited talks by Farhan Saif and Salman Khan Safi. So I look forward to seeing you back here again in half an hour. Thank you again very much, Jibran, and everyone for attending.
Thank you very much. Bye.